everyone, so I'm Yachin. So today I'm going to talk about the causal effect of elevated fasting blood sugar on heart disease. In this research project, our research question is what is the average causal effect of elevated fasting blood sugar on heart disease? In the plain language, we want to know if everyone had high fasting blood sugar vs the normal fasting blood sugar, how much would the chance of heart disease happen or change? To study this, we use the UCI heart disease dataset showing below on here. You can open it. So this dataset has been combined 4 clinical databases from Cleveland, Hungary, Switzerland, and VA Long Beach, and it includes 76 recorded attributes, which is really comprehensive. From the available variables, we mainly focus on 3 variables. For the treatment F, it means the fasting blood sugar. We set F is equal 1 if fasting blood sugar is at least 120 meter per deciliter. And if F was equal 0, it means it is below than 120 milligram per deciliter. And then for the N variable we choose is the heart disease. We define N was equal 1 if the result shows any heart disease, and N is equal 0, it means that no heart disease is present. And for the age, which is a confounder, we can see on here, so it means N was a numerical variable. And now I will briefly introduce about the causal model. So we assume the relationship is a regular relationship. So age can influence the fasting blood sugar, which is old patients are more likely to have elevated blood sugar. So we have an arrow from A goes F. And age also affects the heart disease risk, so we can have A goes N. And this structure means age is a confounder. It has a backdoor path from F, A, and N. If we ignore the age, we would mix up the effect of aging with the effect of fasting blood sugar. To plug this backdoor path and identify a causal effect of F on N, we need to adjust for age in our statistics model. Now I will move on to the third part, statistics model. So for this part, because our outcome N is a binary, so we will use a logistic regression framework, and we will fit separate model for the 2 treatment group. We can see on here the group smaller than 100 and the group greater and equal than 100. So for the patient with F equals 0, it means they are normal fasting blood sugar. We will model Ni goes approximate Bernoulli Pi. Logit Pi is equal alpha 0 plus beta 0 plus Ai. For the patient with F equal 1, elevated fasting blood sugar will model Ni is approximate Bernoulli P2i, and logit P2i is approximate alpha greater than 120 plus beta A2 plus A2i. So in that case, now I'll begin to introduce how we do adjust for the priors. So because I will mainly introduce how we select alpha 0, alpha 1, beta 0, and beta 1. For alpha 0, it is the intercept in the normal FBS group, so we look at typical heart disease risk in middle-aged adult without database. So reasonable baseline risk is around 10%, so then we choose it was logit 0.10, which is equal to negative 2.2. Though we also give a large standard deviations, then this prior should be weakly informative, and then the data can still works with the estimate. And then for the alpha 1, so we're thinking about this are the high FBS group. So according to the resources study suggests, it shows that elevated fasting blood sugar increased the cardiovascular risk moderately. So with like odd ratio around 1.1 to 1.3, so then we'll have log OR. It's approximate 0.10 to 0.16. So we'll roughly use the alpha 0, the initial one, and then plus the change 0.20. So then we got negative 1.9. Therefore, we choose the prior for alpha 1 was logit negative 1.9 and 1.5 square. And now for the beta is the age effect, beta 0 and beta 1. We use the standardized age, so we do not have strong prior knowledge about the exact slope in each group. And then, so we choose the symmetric, weakly informative prior. So in that case, we choose those are 0, 1 square, 0, 1 normal. And now after that, we check on the graph. So from the graph, then we can see it is the weakly informative. Therefore, it shows that we have a good choice on the priors. Those intercepts are good in the cases. Now I will pass to Yizhi for the part 4.
Okay, hi everyone. My name is Yizhi Yang, and now I will briefly introduce about the sections 4 to 6 of our project. Okay, so first let's look at the section 4, the model validation on the simulated data. And before using our Bayesian logistical model on the real data set, we checked whether it can actually recover the unknown parameters in a controlled setting. So we consider two groups matching our causal setup. The first one is f equals to 0 group, and the second one is f equals to 1 group. And for each group, we fix the true parameters, true intercept and the slope in the logistic regression, generated a standardized age covariate, and then simulated the binary heart disease outcome from the corresponding Bernoulli distributions. And we then feed exactly the same Bayesian logistic regression in PyMC, which we will later use on the real data, with also the weakly informative normal price. Also, the posterior means for the coefficients were very close to the true values we set, and the credible intervals comfortably contained those true parameters. Also, the trace plots showed good mixing and no pathologies. So this simulation study tells us that under the realistic sample sizes, our model and the prior choices are capable of recovering the underlying effects. Okay, so now let's go to the section 5. We do some data preparation on the real data. So for the real analysis, we use a UCI heart disease dataset. And from the full set of the variables, we only extract 3 of that match our causal DAG diagram, which are just FBS, NUM, and age, and respectively FN and A. So we then standardize the age again, just as what we did. So now 1 unit of the A standardized corresponds to a 1 standard deviation increase in age. So finally, we split the data into 2 subsets, still f equals to 0 and f equals to 1. And then we use the A standardized and also N in each group as the inputs to the posterior models. So in section 6, we just fit the posterior model on the real data and also do some see the diagnostics. So on the real data, we feed separate Bayesian logistic regressions for the normal and also the elevated fasting glucose groups. And again, they are still done with the weakly informative normal price on both the intercepts and the slopes. So we use MCMC and then summarize the resulting posteriors. In both groups, age has a positive association with heart disease, but the effect in the elevated FBS group, which is f equals to 1, is more uncertain. So this reflecting the smaller sample size in that group. Also, the standard MCMC diagnostics are all satisfactory. The trace plots mix well. All R hat values are essentially 1, and the effective sample sizes are in the thousands. So this means the independence is good. So the section 4 to 6 together show that our model works on the simulated data, the real data, also prepared consistently with the causal DAG, and the posterior inference on the real data set is based on the well-behaved and reliable MCMC output. So this means our model is good. Okay, so now let's go to Chen-Yi to talk about the rest part.
Okay, hi everyone, I'm Chen-Yi Li. I will cover section 7 to 9 about posterior predictive checks, our main conclusion and future work. So in section 7, we do posterior predictive checks separately for f equal to 0 and f equal to 1 groups. The idea is simple. If our Bayesian logistic models are reasonable, then data simulated from the posterior should look like what we actually observed. The results are shown below, and what we see is reassuring. For both groups, the observed heart disease proportions sit close to the posterior means and remain well inside the 89% posterior predictive intervals. So at least at the group level, the model is capturing the outcome rates we see in the data. This gives us the confidence to interpret the causal estimates that follow. Okay, we go to section 8, which is answering the question. We would mainly discuss the first and the last question here, since the second question is actually about section 7. So for the first question, the answer is that the high FPS is associated with only a slight increase in the risk of heart disease, and the data are compatible with little or no causal effect if we condition on age. So for the last question, the answer is absolutely yes. Our conclusions is backed by evidence from 3 places: simulation recovery, clean MCMC diagnostics, and posterior predictive checks. On real data, the observed heart disease proportions are about 0.453 for f equal to 0 and 0.489 for f equal to 1. And our posterior predictive means are close, which are roughly 0.450 and 0.473 respectively, with observed values inside the 89% predictive intervals. So the model supports our claim that the age-adjusted effects of high FPS is small and uncertain. And now we come to the section 8.2, which is about addressing the confounder plus ACE results. To make this concrete, we present 2 versions of risk difference f equal to 1 minus f equal to 0. The first is the crude estimate. So here, the manual ACE has a mean of about 0.036. The distribution is skewed positive with about 67.5% of draws above 0, which might look like a small harmful effect at first glance. Then we adjust for age using our Bayesian model and G computation, and the age-adjusted posterior ACE is essentially centered at 0. The mean is around minus 0.0024, and the mass is almost split evenly around 0, with 47.6% negative versus 52.3% positive. So the story is that the age is a positive confounder. Older patients are more likely to have f equal to 1 and also more likely to have n equal to 1. If we ignore age, we over-attribute part of the age effect to fasting blood sugar. Once we adjust properly, the apparent effect is basically washed out. Now we come to the last section, which is about future work. Firstly, in terms of the limitations, which is 9.1, we highlight 3 directions. The first is omitted variable bias. Our DAG intentionally adjusts only for age, but heart disease is manufacturable. Other available risk factors like sex, resting blood pressure, and could still confound the relationship between F and N. The second is the information loss from binarization. We binarize those exposure and outcome, which discards the continuous glucose signal and the ordinal severity information in the original heart disease label. The last is the generalizability. The dataset is drawn from specific clinical sites, so the findings may not perfectly represent the general population. Lastly, we discussed the possible improvements, which is 9.2 and 9.3. So going forward, we would like to expand the adjustment set, especially sex, resting blood sugar, and serum cholesterol, and possibly add lifestyle proxies like BMI or smoking if available. We could also explore a continuous treatment version of FPS, heterogeneity by subgroups, or even model disease severity with an ordered outcome. So that is all for our presentation. Thank you very much.